This is lesson 3.1 of Geometry, Unit 3. It's called Inductive Reasoning and Counterexamples. So we're really starting into the logic portion. That's the name of this chapter, is logic. Logic portion of geometry. It's one of the courses that forces you to think critically and develop some new pathways around that in the brain. So today we're just going to look at conjectures based on inductive reasoning and then provide counterexamples to prove that statements are false. So inductive reasoning just uses a number of specific examples to arrive at a conclusion. So you just share multiple examples of why it's true to eventually say, all right, we've seemed to have exhausted all of our examples and they're all true, and so the reason must be true. So, or the idea must be true. So a conjecture is just a concluding statement that you reach by using inductive reasoning. And a counterexample is any statement or explanation that proves a statement is false. And it only takes one counterexample to prove false. Okay? Any number of good examples, any number that are true is undone by that one false. Okay? So if you just come up with one reason where it doesn't work or one example where it doesn't work, then that particular idea is false. Okay? So here's example one. Determine if the statement is true or false. If false, provide a counterexample. So you have 3 points, A, B, and C, and the conjecture here is that those 3 points, the conjecture, that's my final concluding statement, is they are not collinear. That's the conjecture. Okay? Well, what this is assuming then is that there's no way I could draw a picture where A, B, and C were all collinear on the same line. Well, yeah, that's pretty simple to do. So here's an example where A, B, and C are collinear, and it only takes one statement to prove that something is false. Now, therefore, this statement is false. Okay, and this is my counterexample, this picture. So this would be my counter example. All right, so that's what we're doing here. And these concepts are geometry related, so sometimes they take a little thought and they may be new to you, and there are things that we're going to build your vocabulary around as well. So here's the next one. If segment AB, it's got a segment bar on the top. I don't know if you can see that. I'll draw a little darker. Segment BC and segment AC are congruent, meaning they're all the same length. If that's true, if they are all the same length, then they must be collinear. That's the conjecture. It's the only way I can have segment AB, BC, and AC be congruent is if they are collinear. Well, I can draw a triangle like this. And I can call this A, and I can call this B, and I can call this C, and I can make AB the same length as BC, which is the same length as AC, by putting these little hash marks on there that indicates they're the same length or congruent, and they are clearly not collinear. In fact, I think it would be difficult for you to draw a picture of where they are collinear if they're congruent. So if you've got, let's say on this line segment here, I split this in the middle, and maybe I make this AB, and this one's BC. Well, those are congruent, but AC is clearly 2 times as long as AB and BC. And so this is clearly a false conjecture. And that's the counterexample. So I want to show a picture where they are not collinear. This other picture, I was trying to show you where they might be congruent and collinear, but you just can't draw that picture. So that was really, really false. Here's one. AB plus BC equals AC. And if AB plus BC equals AC, they're saying that AB and BC have to be equal length. That's what AB without a bar on the top, BC without a bar or line segment symbol on the top of that. indicates that that's length they're talking about. Plus, you wouldn't say AB is equal to BC if it was congruence. You'd put a congruent symbol there. So let's see if AB plus BC has to equal AC. This is really a statement of betweenness. Remember that? Okay, so this is the betweenness statement. So I'll put A here, B here, and C here. And I can simply label this one 1 and this one 5. And that's a true drawing. I have not broken any rules of geometry by sketching that drawing there, and there's no reason why AB can't be 1 and BC can't be 5. So AB plus BC does equal AC, which is 6, but AB is not equal to BC. So this is the perfect counterexample. So again, this is false. Okay. Example 4. If angle 1 is complementary to angle 2, and then angle 1 is complementary to angle 3, then angle 2 and angle 3 have to be congruent. This is the conjecture. Is this true if these other two statements are true? Well, let's draw a pair of complementary angles. In fact, I'll take a right angle like this, and I'll just split it like this. And I'll call this one angle 1 and this one angle 2. So give me some measurements here. Think about the measure of angle 1 and angle 2. What might they be? Well, here's what I know. I know that angle 1, the measure of angle 1 plus the measure of angle 2 has to equal 90. You agree with that? Okay, now let's focus on the second statement. So here's 1 complementary to 2. Okay, I'll put a right angle mark there in the corner. Now let's draw angle 1 complementary to angle 3. So if I do that, I'm going to get this. So here's angle 1 and angle 3. And what I know is that the measure of angle 1 plus the measure of angle 3 also equals 90. Well, can't I just, this is an equation, can't I just move the measure of angle 1 to the other side of the equation by subtracting? Then I get this, the measure of angle 2 equals the 90 minus the measure of angle 1. And then for the second equation, I move angle 1 over there, and I get the measure of angle 3 equals 90 minus the measure of angle 1. That's an ugly looking 1 right there. There we go. So now look at these two sides. Aren't they the same? Well, if those two sides are the same, then the measure of angle 2 must equal the measure of angle 3, which makes angle 2 congruent to angle 3. And it doesn't matter what measure I choose for 1 and 2. Or I could just give you an example. This is called a proof, by the way. I just wrote a proof loosely, right? Hopefully you followed it, but you could do things like just give some pairs. Angle 1, angle 2, angle 3. So if I make angle 1 50, well, angle 2 would have to be 40, and angle 3 would have to be 40. And if I make angle 1 60, then these would both be 30. If I make it 70, they're both 20. Well, can you give me a measure for angle 1 that isn't going to lead to these two being the same value? Yeah, there is no measure. I mean, angle 2 and angle 3 are going to be the same measure no matter what you pick for angle 1. So the exhaustive list would be for you to write every single pair of numbers that add up to 90. Now, you can't do that because numbers, for every two numbers, there's always another number in between. So you can't ever write them all out. There's an infinite number of those. So, but this one is our first true one. This one's true. Okay. And so the nice thing about the true ones right now is you don't really need to justify it to me. Okay. It only says if it's false, you provide a counterexample. Well, I showed you lots of reason here why it's true, and eventually you'll be able to do that as well. Okay, so right now you just need to say, oh yeah, I think that one's true. Okay, so you're going to look at IXL A2. That's going to show you about counterexamples, or it's going to quiz you on counterexamples, and you can find that in IXL.